Welcome back to the Chem OG. Today we're going to be taking a closer look at chirality and some of the effects that it has. And as we talked about last time in our chirality video, we mentioned that chiral centers and their mirror images, even though they have the same four attachments, they're not necessarily identical to each other. So if I take a look at both these molecules, they are mirror images of each other. They have the same four attachments, but they're not necessarily identical molecules. And so what we do need is a way to distinguish one orientation or one-handedness of that molecule from the other. And the answer is going to lie in ways of establishing a particular convention for configuration. And there are two main ways that we label configurations. One is the one that we're going to talk about today, and that is an absolute configuration, using a set of rules called the Cahn-Ingold-Prelog rules, which were established back in the late 1950s. And the other way is take a look at relative configuration. Now, relative configuration we'll speak about in another module, but relative configuration is something that has to do with amino acids and carbohydrates. And so there are certain molecules that it makes sense to take a look at a relative configuration for. Relative configurations predate the RNS or the Cahn-Ingold-Prelog rules. And so because relative configurations still work for the most part, we haven't gotten rid of those entirely, but anything that we use relative configurations for, D and L, we can also use RNS for as well. So quick note before we get into the swing of things with absolute configurations, and that is that chiral molecules display optical rotation, something called optical rotation. They rotate plane polarized light in a particular direction, whether it's clockwise or counterclockwise, and that's something that we measure experimentally through a polarimeter. Now, when a molecule rotates plane polarized light in a clockwise direction, we say that that's dextrorotatory, and we label that with a lowercase italicized d, or we just put in a plus sign. Or if it rotates plane polarized light, if that molecule rotates plane polarized light in the opposite direction, in a counterclockwise direction, we say that that's levorotatory, and we designate that with a lowercase l or a minus sign. Optical rotation can never ever be determined by taking a look at the structure of a molecule. So there's no way that you can take a look at a particular functional group and the way those four things are attached to each other and be able to tell just by looking at the structure of a molecule whether it's going to be plus or minus or D or L. But we're going to be using the orientation of the molecule to be able to determine RNS or relative configuration D and L. So it's important to note that even though we use the same two letters D and L, lowercase d and lowercase l have to do with optical rotation. Uppercase D and L have to do with relative configuration that is based on the structure of the molecule and where the substituents are oriented. And so D and L is not the same as D and L, and D and L lowercase is not the same as RNS. So don't confuse those two. Lowercase d and lowercase l can only be determined experimentally. All right, so today's lesson is going to be about absolute configuration, and we're going to take a look at a set of rules called the Cahn-Ingold-Prelog rules. And the goal of these rules is that two different people looking at the same exact molecule will always be able to come up with the same configuration. So long as we're looking at the same molecule, we should always come up with the same configuration. So it's an unambiguous way of being able to tell the orientation or the handedness of a molecule with which we're presented. CIP rules were never ever intended to take a look at the actual chemistry. And so, in other words, it's not true that the R version of a molecule is more reactive than the S version or vice versa. So these Cahn-Ingold-Prelog rules were never ever intended, nor were they advertised as something that predicts reactivity or optical rotation, as we just mentioned a moment ago. So if you want to know which isomer is more reactive, you're going to have to find that out in the lab. If you want to know which isomer has which optical rotation, or how much it is, or whether it's plus or minus, you're going to have to determine that in the lab as well. So CIP rules have nothing to do with reactivity, have nothing to do with optical rotation. So Cahn-Ingold-Prelog rules are applied in 3 steps. Step 1 is to, well, if you have 3 or 4 different attachments rather to your chiral center, then you need to assign priorities to those chiral centers. And these steps that get to assign priorities to different substituents are ones we can use in other types of isomers called geometric isomers as well. So we'll get to that when we get to it. Step 2, after you've assigned the priorities, is to make sure that the lowest priority substituent is oriented away from you. Okay, so whatever atom is the lowest priority that you assign is oriented away. And then after you put the lowest priority away, you still have 3 more substituents. And so based on the orientation of those remaining 3 substituents, we're going to be assigning either an R configuration or an S configuration to our molecule. So those are the 3 steps. Figure out the priorities of the 4, put the lowest priority one in the back, and then make a trace from 1 to 2 to 3, and then figure out whether that trace that you make from priority 1 to 2 to 3 is in a clockwise or a counterclockwise direction. Now, those are the steps, and those are the, that's sort of the order in which you should apply them. But for many students, probably the more complicated thing is, figuring out the priorities, and that requires a whole bunch of steps in and of itself. And so what I'm going to do is I'm going to take these steps in reverse, kind of show you what RS means, show you what orienting away means, and then apply those rules to the 4 different attached atoms. Okay, so we're going to do things in reverse because, again, the priority rules and figuring those out is the most complicated thing. And I want to make sure that, we have all the other stuff, all our other ducks in a row before we start assigning priorities to the 4 different substituents. So we're going to start with step 3. So in step 3, we're going to assign whether the orientation is R or S. And because we're taking the steps backwards, I'm going to assume that we've already, figured out which one's priority 1, 2, 3, or 4, and that we already have priority 4 in the back. So now we're taking a look at a molecule. We've already determined that, this one's priority 1, this attachment's priority 2, this attachment's priority 3, and we've already determined that attachment 4 is in the back. So how do you assign R and S based on that? Well, what you do is you start and make a trace from priority 1, circle it to priority 2, and then continue the trace on to priority 3. And whether the configuration is R or S is basically going to be determined by how we write each of those 2 letters. So what I'm going to do at the top here is I'm going to write out the letter R. So when I write down the letter R, I'm going to make, a vertical stick, and I'm going to make a loop that comes through and back down. And so if you take a look at the direction in which I made that loop, I made it in a clockwise direction. So that's a good way to remember that when you're looking clockwise, that is the R configuration. The next thing I'm going to do is I'm going to write out the letter S. And when I do write out the letter S, I'm going to be starting at the top right, and I'm going to snake my way down to the bottom like that. And if you notice, when I started to where I ended, I made a counterclockwise trace. So that's a good way to remembering which orientation is R and which orientation is S. So if we're taking a look at the molecule that we have going on right here, when I make a trace from 1 to 2 to 3, that is a counterclockwise rotation. That's more reminiscent of S. So this would be an S configuration. All right. Now I'm going to copy that same molecule, and I'm going to make a slight adjustment to it. And that slight adjustment to this is the following. What if I swap 2 of the substituents on this molecule? So as I take a look at that molecule in the middle of our page there, if I swap priorities 2 and 3, check out what happens to the orientation now. So all I did was I swapped the 2 atoms, 2 and 3. And now the trace that I make, if I make from 1 to 2 to 3, is in a clockwise direction. And so that configuration is now R. Okay. So whenever you swap 2 substituents on a molecule, no matter what the situation is, you will end up with the opposite orientation or the opposite absolute configuration. So I'm going to copy that molecule in the middle one more time, and I'm going to swap 2 more substituents. Let's say that I swap priorities 1 and 2. So they're going to exchange spots. If I retrace from 1 to 2 to 3, so now with the molecule as is, after I've swapped 1 and 2, if I retrace, I'm going to get that orientation. And that orientation is also counterclockwise. So now I reverted the R back to the S. So whenever you swap 2 substituents, this is really important, whenever you swap 2 substituents, that always inverts the configuration. And that gets us to making step 2 of our Cahn-Ingold-Prelog rules a little bit easier, because step 2 was making sure that the lowest priority substituent is oriented away. Now, it's not always the case that your substituent is going to be oriented away, or that lowest priority substituent is going to be oriented away. So for example, if I'm looking at this molecule, the substituent that's on a dash is actually priority 2. That is not the lowest priority. The lowest priority is priority 4. So I could sort of do the mental gymnastics and reorient the molecules such that 4 is the one that's away, or I could just simply swap those two, right? Switch their positions, remembering that what I end up with is the opposite configuration. And so determining the trace for this molecule isn't too bad because 4 is in the back. So I'm going to make a trace from 1 to 2 to 3. And as I make that arrow, I find out that it's the S version of the molecule, which means that pre-switch, that molecule was the R version, and I don't have to worry about reorienting the molecule. So simply swapping two substituents is a really powerful tool to determine what the original molecule's setup was like. All right, so now we've determined how it is that even if the lowest priority substituent is not away, how we can swap two substituents, invert the configuration just to make determining configuration a little bit easier on ourselves. But here's another wrinkle. What about Fischer projections? So in a Fischer projection, and if you're not there yet or you've seen Fischer projections, that's fine. But certainly if you've had a biochemistry class, you've dealt with Fischer projections quite a few times. And so if I'm looking at a Fischer projection is such that the horizontal bonds are on wedges. So each of the atoms to the left and to the right is coming towards us, whereas the vertical bonds are on dashes. So each of those is going away from us. And so how do you determine the absolute configuration around a Fischer projection? Well, the away position is actually the vertical bonds, because those are the ones that are on dashes. So if we take a closer look, and here's a little mnemonic to be able to help you determine what the appropriate Fischer projection is. If the lowest priority substituent is on a horizontal bond, it means that it's not where it's supposed to be, right? Because the lowest priority substituent is supposed to be away. If we put it on a horizontal bond, that means we're looking at it being on a wedge. So this is an example molecule in which the horizontal or the lowest priority substituent is on a horizontal bond. It's not where it's supposed to be. If the lowest priority substituent or atom is on a horizontal bond, one way to remember that whatever configuration you find is not the correct one is that horizontal means horribly wrong. Whereas if the lowest priority substituent is on a vertical bond, then it's very correct. So let's take a look at how we can determine the absolute configuration around these Fischer projection molecules. I noticed that my lowest priority substituent is on a horizontal bond. That means whatever configuration I end up finding is horribly wrong. And so if I make a trace from 1 to 2 to 3, that's going to be in an S orientation. But the molecule that I have has that lowest priority substituent in a horizontal bond. So that means whatever configuration I just found is not correct. It must be the other one. Remember, there are only two possibilities here. So for this particular molecule, be R version or the R isomer of the molecule. If I check out, right, taking a look at the lowest priority substituent, here it's in a vertical arrangement. So if I make a trace from 1 to 2 to 3, that's how my trace is going to look like. That is in a counterclockwise direction. So the configuration I come up with is an S. And since the lowest priority substituent is on a vertical bond, that means I'm going to keep it as is. So that's a quick way to be able to do the absolute configuration of Fischer projections. All right, so we've kind of traced back. We determined how to do R and S. We've determined how it is that we can put our lowest priority substituent away. Now comes the most complicated part, which is assigning priorities to each of the 4 atoms. And when you do assign priorities, it's based on a certain hierarchy. So the first thing you should look for always is the atomic number. So for example, carbon is an atomic number of 6, not 12. 12 is the mass number of carbon. So when we talk about atomic number, what we're referring to is the number of protons. We're not referring to the mass number, we're referring to the atomic number. So look at your 4 different immediately bonded atoms. Not the entire substituent, not the entire chain, only looking at the 4 attached atoms. Figure out priorities based on atomic number. If you have 2 different atoms with the same atomic number, then use mass number as the next rung in terms of the priority ladder. And so for example, if I have 2 carbon atoms, each of those has an atomic number of 6, but if one of them is an isotope of carbon that is a mass number of 13, whereas the other one is a carbon of mass 12, then carbon 13 would get a higher priority than carbon 12. And so where things get complicated, especially with organic molecules, is when you have several carbon atoms attached to your chiral center, and all of them are carbon 12s. So the atomic number is the same, the mass number is the same. What do you do then? So if you do have 2 or more identical attached atoms, then what you want to do is you want to move 1 atom over to find a point of difference. And if 1 atom over isn't going to cut it, then move 2 atoms over, and so on and so forth. Okay, there has to be a point of difference, because remember, the reason that carbon is chiral is because we've determined that there are 4 different substituents. So they have to be different in some way. So let's take a look at an example molecule of cysteine. So if I take a look at cysteine, I'm going to redraw cysteine explicitly with the hydrogens. Okay, so it's a good idea as you're learning to do absolute configurations and as you're becoming more familiar with how it is that you are going to determine the absolute configuration, write out all the hydrogens explicitly. So we're going to take that structure with the hydrogens put in explicitly, and we're going to determine a little bit of absolute configuration awesomeness. And so if I take a look at my chiral center, the carbon to which 4 different things are attached is this one right here. All right. If hydrogen is ever one of your substituents, just assign it priority 4, because there's no way that you're going to have a substituent whose atomic number is lower than 1, right? And hydrogen's atomic number is 1. And it's also the case that, the regular version of hydrogen has a mass number of 1. You can't have a mass number lower than 1 either. So if one of your attachments to the chiral center is a hydrogen, just label that as priority 1. Now, I have 3 more substituents, or 3 more atoms of which I need to, make myself, or for which I need to assign priorities. And that is, I have a nitrogen, I have a carbon, and I have a carbon. Notice I mentioned nitrogen and carbon and carbon. I didn't say carboxyl group. I didn't say, this methylene thiol. I didn't mention ammonium. I'm just taking a look at immediately what's attached. And what I have immediately attached is nitrogen, carbon, and this carbon right here. So between a nitrogen and a carbon, nitrogen has an atomic number of 7, whereas the carbons have atomic numbers of 6 and 6. And so that means that nitrogen is going to be priority 1. Now the next thing I need to determine is, I'm going to take a look at each of these carbon atoms right here, and I recognize that both of them are identical to each other. And so in that case, what I want to do is I want to write out the 3 adjacent atoms to that carbon from highest atomic number to lowest atomic number. Okay, so the idea is I'm going to take a look at this carbon right here and determine what is immediately attached to it other than the chiral center itself. And the reason I'm ignoring the chiral center is because both this carbon and this carbon are attached to that same chiral center. And I'm interested in finding points of difference, and the chiral center is not a point of difference between them. And so if I take a look at the carbon on this side, this carbon is bonded to an oxygen with a double bond. So what we do is we count that double bond twice. And so I'm going to write down oxygen, oxygen, and oxygen. And I'm going to write that out 3 times. O, O, O. And the reason that I'm not including the hydrogen is because the hydrogen is not immediately bonded to that carbon that I'm interested in. It's bonded to an oxygen. So again, be careful that you're not going too far down the line. Only look at the atoms that are immediately attached and nothing else. Now, let's take a look at the carbon on the left-hand side. This carbon is attached to a hydrogen, and a sulfur. Those are my immediate attachments. And I'm going to write things down from highest to lowest atomic number. So I'm going to write down SHH is what I'm going to write down. All right. So take a look at each of your carbon atoms, find the 3 attachments other than the chiral center itself, and write those out from highest atomic number to lowest atomic number. And the reason that's important is because the next step is we're going to compare those 3 attachments, okay, one by one until we find a point of difference. So I'm going to compare the highest atomic number here to the highest atomic number here. The highest atomic number attached to this carbon is a sulfur. The highest atomic number attached to this carbon is an oxygen. The atomic number for sulfur is 16. The atomic number for oxygen is 8. And so the carbon on the left actually has higher priority than the carbon on the right. Notice that I didn't take into account all of the attached atoms. I didn't say I'm going to add the oxygen to the oxygen to the oxygen, and that makes an atomic number of 24, and I'm going to add the sulfur to the hydrogen, and that makes an atomic number of 18. That's not the way these rules work. The way the rules work is you take a look at the attachments and you figure out, hey, what's the highest atomic number, period, right? Kind of like how we did with the nitrogen and the 2 carbons here, right? What we did was we determined the nitrogen by itself versus this carbon by itself and this carbon by itself. We didn't go farther down the line or anything like that. So that means that our configuration is such that if I make a trace from 1 to 2 to 3, the arrow looks like this, and that is a clockwise direction. And so that means that the absolute configuration for this molecule is an R. All right. So you may be wondering, okay, what if I compare the two immediate carbon atoms and both of them turn out to have the same exact attachments? Well, if all three atoms are identical, then you move on to the next one and then you determine the same thing again, right? Or you write out the three other attachments and you compare those to each other, and then you keep doing it until you find a point of difference. Thank you for watching today's lesson. Don't forget to like and subscribe.